Now we're next going to consider some algebraic approaches for solving systems of linear equations. And as you just saw in this module, using the graphing method for solving systems is often not satisfactory because, number one, it takes a lot of time to graph the lines, and number two, the major drawback is the potential inaccuracy. If x and y turn out to be decimal or fractional values, it's very, very difficult to estimate what those values can be from a graph. So the first method we're going to look at is the substitution method. And so we have the system 2x plus 4y equals 10. And 4x minus 2y is equal to 6. And what we're going to do is take one of the equations and solve for one of the variables, then take that expression and substitute it for that variable into the second equation. Now as we look at the two equations, I don't think there's any particular advantage to either equation solving for either x or y, so I'm simply going to make the decision to take the first equation and solve that equation for x. So let me rewrite the equation here. So we have 2x plus 4y is equal to 10. So I'm going to subtract 4y from each side. Then if we take and divide every term here by 2 then, we end up with x being equal to 5 minus 2y. So what we'll do next now is take this expression for x, then we're going to substitute it into the second equation. So what we're going to do then is to take this and substitute it for x up here in this equation. So we'll do that next. So then we're going to have 4 times the quantity 5 minus 2y, and minus 2y is equal to 6. We'll distribute the 4 and we'll have 20 minus 8y minus 2y is equal to 6. Then 20 minus 10y is equal to 6. And then we'll subtract 20 from each member, so we have negative 10y then is equal to negative 14, or y is equal to negative 14 over negative 10. And if we reduce that, that will reduce then to 7/5. So now we have the y value, and what we'll do next then is to take the value 7/5 and we'll substitute it then into this equation to find the value for x. So we'll do that next. Continuing then, we just found that the value for y is 7/5, and you recall that earlier we solved the first equation for x, and so we had x is equal to 5 minus 2y. So what we'll do now is take this value for y, which is 7/5, and we'll substitute it then in for y in this equation. So let's do that next. So then we'll have x is equal to 5 minus 2 times 7/5. We have then 5 minus 14/5. And getting a common denominator then, we have 25/5 minus 14/5, or x then will be equal to 11/5. And what we'd like to do then to end up is to express the solution as an ordered pair. And we'll, of course, place the x value first. It'll be 11/5 then, and 7/5. Now because this is a single ordered pair, that's going to tell us that the graphs of the two lines in the system will intersect in just one point, which means we have a consistent and independent system. Now it's always a good idea, if you have the time, to go through the check, and what that would mean is we would take the values for x and y and substitute them into each equation to see if we have a true statement. So let's go through the check for the first equation. So let me rewrite it over here. So we have 2x plus 4y is equal to 10. And so we'll then substitute for the x 11/5. And for the y, we'll substitute 7/5. So we then have, what, 22 fifths here, plus 28 fifths. And that will produce then 50 over 5, which will simplify to 10. So we've shown that the ordered pair 11 fifths, 7 fifths does indeed check in the first equation, and I'll leave it to you to check in the second equation.